Welcome, everyone, to this explainer. Let's just jump right in, because today we are looking at something that is quite literally the master blueprint for digital literacy, number systems and codes. If you've ever wondered how our chaotic, unpredictable physical world gets translated into the pristine, perfectly ordered universe of digital logic, well, this syllabus is your ultimate roadmap. Okay, let's dive into this. Right at the top of our source material, we see a statement that really sets the stakes for everything we're going to cover today. It states clearly that this knowledge is absolutely crucial for understanding data representation, compression, and error detection and correction. Now, I want to emphasize, these are not just academic buzzwords. This is the very foundation of every single text message you send, every high-definition video you stream, and every file you securely zip and store. Honestly, without these underlying systems, digital communication just completely falls apart. So here's our mission briefing for today. First, the digital logic foundation. Second, decoding essential number systems. Third, fundamental digital coding schemes. And fourth, outcomes and self-learning. All right, part one, the digital logic foundation, laying the concrete. Our primary learning objective here is incredibly straightforward, but man, it runs deep. We are expected to apply number systems and codes in digital logic. This is the core bedrock of everything we're about to unpack. We aren't just here to memorize textbook definitions, right? We are here to learn the absolute fundamental rules of how digital circuits actually think and operate on a day-to-day basis. And why exactly do we need to apply them? Well, take data representation, compression, and error detection and correction. When we connect these academic objectives to our everyday tech reality, it all suddenly clicks. This is exactly how a massive photograph gets shrunk down to fit on your smartphone without looking terrible, or how your computer instantly knows if a file was corrupted while downloading over a spotty Wi-Fi connection. Grasping this theory isn't just about passing a course, it's practically a superpower for understanding the modern technology you use every single day. Let's move on to part two, decoding essential number systems. Now, what's really interesting about this is how these concepts are deliberately organized into two distinct buckets. Over on the left, we have number systems, so that's binary, octal, decimal, and hexadecimal. Then on the right, we have codes, gray, BCD, XS3, and ASCII. By looking at it this way, we're essentially separating the mathematical languages from the actual representation formats. It's a really brilliant way to structure our thinking as we move forward. Let's look a little closer at those number systems. These are essentially the native tongues of the machine. Now, you and I, we're pretty much stuck on decimal. We've got 10 fingers, so base 10 just feels totally comfortable, right? But computers, they don't have hands. They have electronic switches. So if we want to program them, we literally have to learn to speak their native tongues: binary, octal, and hexadecimal. These are the specific mathematical bases that make digital architecture actually function efficiently. But of course, it's never enough to just speak the language, is it? We have to be able to do the math. According to section 1.1 of our blueprint, the required arithmetic includes binary addition and subtraction, specifically utilizing the ones and twos complement method. It also outlines octal and hexadecimal arithmetic operations. Now I know, twos complement might sound a little intimidating at first glance. Actually, scratch that. It sounds very intimidating. But it's really just a remarkably clever trick that computers use to handle negative numbers without needing a physical minus sign. It's incredibly elegant, and mastering it is a strict requirement for doing digital logic. Comparing these two illustrates a vital distinction we need to keep in mind. Number systems are all about mathematical operations and bases, so how the computer calculates and crunches the numbers. But codes, which we're going to look at next, focus entirely on fundamental schemes for data representation. Basically, if number systems are the math, the codes are the wiring and the translation manual. This comparison perfectly bridges the gap between calculating the data and representing it. Which brings us to part three, fundamental digital coding schemes, packaging data. Here in section 1.2, we find our essential codes: gray, BCD, XS3, and ASCII. I know, this list looks a bit like alphabet soup, but I promise you, these aren't just random acronyms thrown together. Take ASCII, for example. That is the exact reason the letters you type on your physical keyboard actually show up correctly as text on your digital screen. Or BCD, binary coded decimal, which is a highly specific way to encode decimal numbers so machines can read them without complex conversions. These are the fundamental coding schemes used constantly in digital logic to guarantee the data means exactly what it's supposed to mean. And finally, part four, outcomes and self-learning. bringing it together. So the crucial point is the syllabus explicitly carves out a specific topic just for you: error detection and correction codes. This is designated as your independent study, and honestly, its importance just cannot be overstated. In the real world, data gets corrupted all the time. Hardware glitches, signals get interference, files drop. This self-guided topic is where you're going to discover how digital systems actively catch those random mistakes and fix them on the fly, maintaining absolute data integrity. It is, for sure, the safety net of the digital world. So, let's walk through this final journey to see what your success actually looks like. Step 1 is conquering that self-learning topic on error correction. Step 2 is mastering number system arithmetic so you can truly appreciate its role. And finally, Step 3 is successfully applying these fundamental coding schemes to real data representation. Nailing these 3 steps means you have completely conquered the master plan laid out in this syllabus. Before we wrap up this explainer, I want to leave you with a thought directly inspired by that crucial self-learning topic. We've seen just how perfectly ordered and meticulously designed these number systems and codes are. But if our error detection codes were to just fail, what actually happens to all of our perfectly compressed, flawlessly encoded digital data? It's a fragile, absolutely fascinating ecosystem, and mastering this material is the only way to truly understand how it stays alive. Thank you so much for joining me today, and happy learning!